Dear ladies and gentlemen, my name is Артемий Новоселов, and today I will be presenting to you our project SEDENOS, short for Separating and Denoising Seismic Signals with Dual-Path Recurrent Neural Network Architecture. This talk will be structured as follows. I will give you some introduction. I'll explain what kind of data we use and what is the source separation. And we'll quickly go through what is machine learning and what type of architecture this dual-path recurrent neural network is. And then I will present you some results on denoising and source separation and try to explain how and why does it work. And in the end, I'll draw some conclusions. Many seismologists that when we record our seismic data, when we record earthquakes, we often record them with a lot of noise. So consider those two examples. We have two noisy records of earthquakes where P and S phases are colored with red and blue accordingly. It's not the worst case, but still it's considerable. Can we do something about this noise in the data? Well, to answer this, first let's review what kind of data we use. We use the Stanford earthquake dataset, a global dataset of seismic signals for AI, which contains a large amount of seismic data, earthquakes recorded, and a large amount of seismic noise data, meaning just whatever was recorded at the station when there were no earthquakes. This dataset is rather large. It contains 1.2 million labeled waveforms. So what is source separation? Let's consider a noisy seismic record. One way to think about it is that this record contains both signal and noise. So in a sense, it is a mixture of signal plus noise. We have developed lots of useful ways to deal with this problem. Let's consider a case where we have only a single one-component seismic station and we record some earthquakes on it. So we would take a noisy signal and we can do frequency filtering. For example, we can apply a high pass filter and a low pass filter, in a sense separating this low frequency noise from the high frequency earthquake. The other thing we can do is, like, if we take a waveform that seems to have two signals in it, we can separate them in time. Like, we can say, okay, the first signal ends at this particular time and the second signal starts at that time. But what if this frequency and time are overlapping in this signal? Let's consider a case where we have signal 1 and we have signal 2, and what we record on the seismic station is a mixture of those two. And they are not separated in time. They're not separated in frequency. They're overlapping. Can we do something about it? And apparently the answer is yes. We can train a machine learning. What does it mean to train a machine learning algorithm? So let's consider that we have two signals, some input signal and some input noise. We mix them up together to produce a mixture, and then we feed this mixture into machine learning that I will talk about later, and we task this machine learning to output signals and noise separately. Every time it does output something, we compare this output with the input signal and we compute a residual, meaning like how similar those signals are. If those signals are not similar, we basically ask this machine learning algorithm to go through another set of examples and repeat the process of training. So on the right-hand side, you can see the residuals as they get smaller and smaller and smaller the longer our machine learning trains, and sort of a plot of a loss function. Essentially, this is like how good are we at producing exactly the same signals from those mixtures. By same, I mean like that they're similar to the input source. So we used a particular type of machine learning called the dual-path recurrent neural network, and it consists of 4 parts. It has an encoder, a separator, a mask estimation module, and a decoder. So we take two records, we combine them together to get a mixture, and then we feed this mixture into the machine learning. This machine learning algorithm encodes this data in some higher dimensional representation that we're going to talk about later, and produces masks, essentially saying like what part of those encoded features should be taken and what parts should be left out. When we then multiply these masks with the encoder, we would get a signal, predicted signal for source number 1 and source number 2. Then we would compare those signals and repeat the process as many times as needed to obtain a good quality. On the left-hand side, there is a real example of our machine learning framework. So let's see the results. Let's consider that we have some input signal and some input noise, second and third row on the figure. Then we combine them together to produce a mixture. And we ask our neural network to output what it thinks the signal number one is and what it thinks the noise is. And as you can see, it seems like it actually sort of extracted the signal from the mixture even better than the input signal was. Like it basically denoised it much better. On the right-hand side, one can see the residual. But okay, maybe it's not really fair to look at one individual signal. Can we measure it somehow qualitatively? And we can. We can measure a signal-to-noise ratio for each of those mixtures and see if it's improved after being processed with our dual-path recurrent neural network. So on the distribution plot, one can see a distribution of signal-to-noise ratio in some test data set as it is, like no processing being applied whatsoever. Then we compare it to what signal-to-noise ratio we would obtain if we would apply a high-pass filter of 1 Hertz and 5 Hertz, blue and black line accordingly. And then we compare it to the signal-to-noise ratio we would obtain if we process it with our dual-pass recurrent neural network, which is shown in green. And one can see that it is considerably better. Signal-to-noise ratio, the higher it gets, the bigger the signal to noise ratio, and like the better it is. If we can denoise signals this way, can we perhaps separate them as well? Can we perhaps take several different signals, combine them together, and separate them without consideration that one of them is a noise and the other one is a real signal, just separating two signals? Why might it be useful? Example given, aftershocks. It's quite often that aftershocks overlap, and there is an opinion that we don't detect many aftershocks because they are overlapped on top of each other, and we're just not able to see the individual aftershocks at all. So let's see the results. We take some input signal number one and input signal two. We combine them together to form a mixture in the first row, and then we ask our neural network to output what it thinks the signal one in this mixture and signal two in this mixture. We check the residual plot. Looks fairly good. Like there is some residual left, but look how similar signals are. They are really, really similar. And look at the input mixture. There is no way how one can separate those signals from a single station of one component using frequency analysis, phase analysis, whatnot. It's just not going to be separated. So why might it work? Let's consider again that we have some input signal. We feed it to the machine learning. What does machine learning output? It essentially outputs features. Like we as humans can compute some features of the signal. We can compute the spectrum, we can compute the phase, we can do some Hilbert transform and whatnot. In the machine learning terms, we wouldn't be able to interpret what those features mean, but it's essentially a similar thing. So then we can combine all of these feature vectors into a feature matrix, which is essentially the encoder. Like this encoder's representation that I showed earlier, it's essentially just a bunch of features that are added together. And then this machine learning separates signal not based on one feature like phase or frequency or time, but a sort of a combination of all of these features together. And it learns to do so by looking at a really large amount of data. So sort of learning how statistically those features are distributed for each individual signal and how statistically those features are distributed for a mixture of those, and trying to optimize to feed both distributions at the same time. So to conclusion, we trained the neural network with seismic data from the data set. We applied the source separation neural network to denoise the data. And also we show that we can separate two earthquake signals. We then consider some cases like aftershock analysis. Would that be useful? And it seems like it would be useful in many areas like induced seismicity and seismoacoustics, where many different ways need to be distinguished. Besides that, signal-to-noise separation might be useful for other things. Example given for better defining earthquake phases, since it's easier to pick those phases on a record with low signal-to-noise ratio. I mean, with a high signal-to-noise ratio. Besides that, signal-noise separation might be useful for other things. Example given for better defining earthquake phases, where signal-to-noise ratio should be high to give someone the ability to distinguish those phases confidently. And it also might be useful in ambient noise tomography, where when one is often interested in keeping just the noise part of the data without any deterministic signal in it. We also provide a reproducible research repository on a GitHub where you can download the code, you can use this machine learning to denoise and separate your own data. And we provide all the scripts how to train such a network and so on and so forth. And we also provide a preprint on the Earth archive. And this publication is currently under consideration for GGR Solid Earth. We took this idea from the speech domain, where such networks were used for separating two speakers, known as a cocktail problem, or separating different musical instruments in a song, and so on and so forth. And we applied it to the earthquake data, and we showed that it worked. So we think that it might also work with any waveform data in general, and it might be useful for medicine and for other types of waveform data. Thank you for your attention. Please reach out to me on the email or on the GitHub or elsewhere if you're interested. And thank you very, very much for listening today.